All right, let's talk about an invisible problem that could be quietly costing you money and, frankly, wrecking your equipment. We're talking about electrical noise. So let's dive right in and figure out how to clean up your power.
You know that sound, right? That weird buzzing from a transformer, or when a piece of gear feels way too hot for no good reason. Yeah, that's not just your imagination. It's a real symptom of a hidden problem, and it's costing you money, wasting energy, and literally shortening the life of your most expensive equipment.
So what exactly is this invisible culprit? Well, we're talking about a kind of electrical pollution called harmonics. Let's break down what they are and, more importantly, where on Earth they're coming from.
Okay, so our power grid is designed to give us this perfect, smooth sine wave of electricity, right? Usually at 50 or maybe 60 hertz. Harmonics are basically these unwanted rogue frequencies that are multiples of that main frequency. So you've got the third harmonic buzzing along at 150 hertz, the fifth at 250 hertz, and on and on. Think of them like ripples messing up a perfectly calm lake.
And this is what you get. When you start adding all those little harmonic ripples onto the original clean wave, you end up with this distorted, jagged mess. It almost starts to look like a square wave. And this messed up power, it isn't just ugly to look at, it's incredibly inefficient, and it's actually doing damage.
So where is all this distortion coming from? Just look around you. It's generated by stuff we call non-linear loads, and that includes, well, almost everything modern. From the big variable speed drives in factories, to the computers and UPS systems in your office, and even the ballasts inside fluorescent lights.
But the number one culprit? It's the simple rectifier circuit. I mean, think about it. So much of our modern electronics runs on DC power, so they're all constantly converting AC from the wall into DC. The problem is, that conversion process isn't smooth. It draws current in these short, sharp bursts, and that injects a ton of that harmonic noise right back into the grid.
Okay, so we've got this electrical noise. Big deal, right? Well, yeah, it is a big deal, because the symptoms are serious. They range from just, being inefficient all the way to catastrophic equipment failure.
The big one is heat. Harmonics generate a lot of extra heat, and this thermal stress is literally cooking your transformers, your motors, and your cables from the inside out. All that heat is just wasted energy, and it means a drastically shorter lifespan for your gear.
And that heat leads directly to our next problem: terrible efficiency. Motors don't run as well, and your power factor, which is just a fancy way of saying how efficiently your system is using electricity, it just tanks. This means your whole system has to pull more power from the grid just to do the exact same amount of work.
And what's the end result of all this stress and heat? Well, stuff breaks. The constant strain from this distortion can fry sensitive electronics, it can make capacitors literally burst, and it causes all sorts of weird, mysterious malfunctions that are an absolute nightmare to track down.
So you can really think of the damage in two ways. In the short term, you get those super frustrating problems like circuit breakers that trip for no reason or weird interference on your communication lines. But the long-term effects are even more damaging. It's that slow, steady overheating that just wears down your equipment over time, leading to fatigue and eventually failure.
Okay, that's enough of the bad news. We get it, it's a problem. So now let's talk about the fun part, the solutions. How do we actually clean up this electrical pollution and get back to that nice, clean, efficient power we want?
The good news is, engineers have come up with a whole toolkit to fight this stuff. We've got everything from really simple, cheap add-ons to some seriously sophisticated electronic solutions. This table gives you a pretty good overview of the main options. On one end, you've got line reactors. They're simple, they're passive, and they're definitely the most affordable place to start. In the middle, you've got smarter designs like 12-pulse rectifiers. They're more built-in, a lot more effective, but yep, the cost goes up. And then at the high end, you've got active filters. These are the real heavy hitters. They offer incredible performance for really critical stuff, but they also come with the highest price tag. It's always a trade-off between performance and your budget.
So let's start with the basics, a line reactor. Honestly, this is pretty much just a coil of wire, an inductor that you put into the circuit. It basically acts like a shock absorber for the electricity, smoothing out those sharp pulses of current and knocking down the most common harmonics. It's a simple, tough, and super cost-effective first line of defense.
Okay, next up is a much more clever design, the 12-pulse rectifier. This thing uses a special transformer to feed two separate rectifiers that are deliberately set out of sync with each other. And the result is pretty slick. The worst harmonics made by one rectifier get canceled out by the other one. It's a really smart way to tackle the problem right at the source. And finally, we have the high-tech approach, an active filter. This thing is brilliant. It works almost exactly like a pair of noise-canceling headphones. It's constantly listening to the power line for any harmonic distortion, and then it injects the exact opposite, an anti-harmonic current, to cancel it out in real time. All that's left is that pure, clean waveform we want.
Theory is one thing, but let's see how this stuff actually works out in the real world. We're going to look at a super common industrial setup and see just how effective these fixes can be.
So here's our setup. A standard 400-volt system that's powering a 150-kilowatt variable speed drive. You know, the kind of thing you'd find running HVAC systems or big industrial pumps. This is a classic source of harmonics.
And no surprise, when we hook up the meter, we find the total harmonic distortion, or THD, is sitting at 7.7%. Now, most standards say you need to be under 5%, so this system is officially non-compliant. It's polluting the grid, and it's stressing out its own parts.
So what's the fix? Well, let's start with the simplest solution. We're going to install a 4% AC line reactor. This one simple component immediately gets to work smoothing out that jagged current draw from the drive.
And look at that result. The total harmonic distortion plummets all the way down to 4.0%. Just like that, with one simple and relatively cheap component, the system is now compliant, it's more efficient, and it's under way less stress. That is a huge win.
But of course, every engineering decision is a trade-off, right? That simple line reactor is by far the cheapest option. If you move up to more advanced solutions like 12-pulse rectifiers or especially those active filters, you're going to get even better performance, but you're also going to pay a significantly higher price. The right choice always depends on what the application actually needs.
So what's the bottom line here? The best way to think about harmonics is like a hidden tax on your power system. It's this invisible drain created by all our modern gadgets that wastes money, cooks your equipment, and causes all those mystery failures. But the good news is, once you understand the problem, you can use these practical, cost-effective methods to fight back, protecting your investment and making everything way more reliable. See, getting harmonics under control isn't just some abstract theory. It's about protecting your gear and saving real energy. It's a critical step for any healthy, efficient power system. If you want more deep dives into the real-world engineering that powers our lives, make sure you subscribe. Thanks for watching.